So another inscription problem. This time we have a rectangle that's being inscribed in a semicircle of radius 3. So let's pause here for a moment and let's just draw ourselves a nice picture. So what we have is we have a circle, a semicircle of radius 3. Okay, so there's our semicircle of radius 3 right there. And then what we're going to be doing is we're going to be putting a rectangle inscribed in that. So that basically means we have something of this nature. So there is our rectangle inscribed in that shape. What we're going to do is let P, X of Y be a point on the circle, and it has a vertex of the inscribed rectangle. So that just basically means there's our P of X, Y. Of course, due to symmetry, we know that this point over here is P of negative XY. Right? So basically, one of our vertices of the rectangle coincide with the semicircle. So that's basically all that's telling us. And so what we want to do is find the area as a function of x, and that's the area of the rectangle. So what do we know about a rectangle? Well, all rectangles are length times width. Right? So there's our rectangle. And then what we want to do in terms of what we have here, right, what is the length and the width in terms of this picture? Well, the width clearly, right, is y, right, the y distance that we have. So we're going to call that y. The length, when we look at the length, we're going to go an x amount this way and a negative x amount that way. So the entire length is actually 2x. And so there is our area of this formula, all right, of this rectangle for the situation that's given. So in terms of x's and y's, we have our length and our width. So there's what we're going to be trying to maximize in a moment. Where's the constraint? Well, if you reach back in the archives, what do we know about a circle? X squared plus y squared, in this case, would equal 9, the radius squared. So if we solve for this, y squared equals 9 minus x squared. We take a square root, we end up with 9 minus the square root of 9 minus x squared. Since we're assuming that this is a top half of a semicircle, we're just going to consider the positive square root of 9 minus x squared. And so there's what I'm going to come up here and replace that y with. So our area is 2x, the square root of 9 minus x squared. And so there is our area of our inscribed rectangle in that circle of radius 3. And so we can now begin to answer questions based off of that. So number one, what's the area when x is equal to 2? So a of 2, when I plug that in there, would be 2 times 2, square root of 9 minus 2 squared. 2 times 2 is 4. We're going to get the square root of 9 minus 5, which is 4 square roots of 4, which is 4 times 2. We get an answer of 8. So that's a pretty nice answer there for that. Oops, you know what? I screwed up. That's 4, makes that 5. So it is not nice, right? So we get 4 square roots of 5 as our area. So when x is equal to 2, roughly about right there, right, that would make that negative 2. The area of that rectangle is 4 square roots of 5. Is there an implied domain of this function? And the answer is yes. Since we're basically constrained by the circle that goes from negative 3 to 3, then we're just going to consider this from negative 3 to 3. That's all we can consider because we're constrained by that circle of radius 3. And then as far as maximizing it, we're going to definitely turn to our calculator because this is not a quadratic. So we're going to input that function and we're going to start to see some high points and low points. In this case, high points because we're trying to find a min. So we're going to turn our calculator on. We're going to clear that out and put in our new function. So it's, what was it again? 2x, right, times the square root of 9 minus x squared. So there's our function. I'm also going to mess around with our window. Since we're going from negative 3 to 3, how about I just go from negative 5 to 5 along the x-axis? Okay, and then let's make that negative 10 to 10, just kind of see what happens. So there's the function. Now we're getting two different things here. Of course, this guy doesn't really make any real world sense because our area is going to be positive, so perhaps we needed an absolute value, but there is symmetric about the origin. All right, so if we can find that high point, then we know that where that low point is. So that x value on this side and that x value on this side would pretty much give us the same area. Okay, so I guess really our restriction is from 0 to 3, right? Because we want to make sure that we have a nice positive area. So let's find that high point. So we're going to go to calculate. We're going to calculate the value. Oops, no. Actually, we can do that. Here's the value at 2, right? So 8.944, which is essentially 4 square roots of 5. But back to the second calculate, we're going to calculate a maximum. We got to move to the left of that point, got to move to the right of that point, and got to move to the point itself. So picture-wise, we're looking at something like this, and the point we find is x is roughly 2.1213, and the area, that's what the y represents in this, is equal to 9. So if x is 2.1239, then the area, right, so if we go just past 2 here, the area of that rectangle will be 9, and that's the largest area that we can find of a rectangle given those conditions. So pretty unique that it's a nice perfect number there. And again, you see the rhythm. So we have our inscribed shape. That's basically our constraint. We have the shape that's inscribed. So we find this in this case it was a rectangle. So we take our area of a rectangle, we replace the length and the width with the x and the y that we have in our picture. Use the constraint to replace y with what it's equal to, and that pretty much gives you a function of x. And then once we have that function of x, we can do all our analysis. We can talk about implied domains, we can find areas at specific locations, and we can find largest values and optimize our equation. So practice those. Again, I think the homework set has a few of them. What's also nice is they have a nice picture already there for you, so you can kind of just use their picture. But just in case I'm wrong about that, right, just read the problem carefully, start, piece by piece, draw yourself a nice picture. Of course, if you're not sure, you can always discuss it on Canvas and make sure you get everybody's input. So there is basically our inscribed area optimization problems. Now you guys need to go practice and get better at it. We've got one more set coming up. Talk to you guys then.